and the problem of time. William gave a pedagogical presentation of dressed observables, first in QED and then in perturbative quantum gravity. Daniel gave a great overview of global symmetries, boundary observables, and the information paradox. Kasia then presented us an inspiring insight into non-local observables, in particular in the framework of algebraic QFT. And finally, Renate gave us an insightful talk about candidates for non-perturbative observables in quantum gravity, and in particular those that can potentially be generalized to discrete settings. So we've decided to schedule a final panel today in order to bring these viewpoints a little closer together, hopefully. And we've also titled the panel discussion From Observables to Observations with regards to what will be the next topic of this series. And of course, I understand that this is a tall order, but in the end, I guess we can all agree that that's what we jointly have to achieve in quantum gravity. So I hope that all of you participants will find the discussion stimulating. Personally, I certainly am very much looking forward to it. And before we start, let me say some brief words about the setup. So Renate, Kasia, Daniel, William, and Philipp have kindly agreed to give us brief reminders and also each other brief reminders of the main takeaways and the key open questions that they have. We will then give them the opportunity to identify open questions and shared ideas amongst each other for like 10 or 15 minutes. And then all of you are very much encouraged to join the discussion with your questions, with your diverse viewpoints, and with new insights and ideas. And hopefully in this way, we can all make a little bit of progress towards this larger question. And you can enter the discussion in many ways. If you can't wait with your contribution, you can already put it in the Zoom chat. You can use the Slack channel. There's also an anonymous questions form, which I can repost or someone of the co-organizers can repost that maybe. You can enter the event number there, and then you can post anonymous contributions. And of course, you can always just raise your virtual hand, and I'll try to keep track of all of those, and apologies in advance if your contribution is somehow lost. All right, and with that, I guess we can start with the brief reviews, and I would start with Renate and then go backwards in the order of the talks. So Renate, you wanted to briefly share a slide, right?
Yeah.
All right.
So let me try and find it. Is this visible?
Yes.
Hang on. Is it visible with all my crap around? Window. I want to go to full view. Yeah. Okay. Yes. So we've seen, as was just said, an interesting cross-section of views on observables in quantum gravity. So if maybe not full consensus, at least I think there was one point of broad agreement, namely that the non-local nature of observables is what makes gravity special and sets it apart. So when discussing quantum observables in quantum gravity, standard notions from quantum field theory on fixed, flat or curved backgrounds are no longer applicable and or appropriate. So microcausality was mentioned by various people. Also the notion of a reference frame that of course frequently appears strikes me as something that's very classical and maybe of doubtful use in a context of a strongly fluctuating kind of Planckian scenario where of course there is no kind of rigid things you can refer to. Everything will be interacting and dynamical. So it's also worth pointing out, as some of the comments from the audience also said, that this is not exactly a new discussion. So some of these were discussed, from the 60s onwards. But of course, it appears in new contexts, and it's also worthwhile re-examining some of these. One of the lessons from the old days was that a discussion such as that about the observables in quantum gravity cannot be looked at separate from kind of the UV issues of quantum gravity, in a non-perturbative regime. That means primarily, what you have to say something about how diffeomorphism symmetry is implemented or represented in this non-perturbative regime, and how it is compatible with renormalization that is expected simply to be needed to take care of the divergences that appear. So these are not present typically in finite dimensional toy models, which one likes to use because they're easy to compute with. So there should be a degree of caution there. So it is a point. So non-locality, I would say, is a feature rather than a problem, and it should be embraced. And this is a tenable point of view. I presented in my talk, DT, CDT quantum gravity models as providing blueprints that starts actually with just two-dimensional Liouville gravity, which you can re-express, via dynamical triangulation. So we're talking about having dynamical lattice regularizations that are completely compatible with diffeomorphism invariance. Indeed, diffeomorphism invariance becomes kind of labeling invariance. So it doesn't interfere at all with renormalization. And you do have renormalized observables that remain finite in a near Planckian regime and meaningful. So examples are the spectral dimension, observables constructed from the new quantum Ricci curvature, but also you have just a notion of diffeomorphism invariant endpoint functions. Of course, it's also true that in the end, we want to link that world of full non-perturbative quantum gravity to that of classical, semi-classical gravity. And I would say, early universe cosmology is kind of a prime example where we want to connect the two things. So here I emphasize that one needs to manage expectations in the sense that your kind of favorite fine-grained feature of some arbitrary, classical solution to GR will most likely not have a quantum gravity equivalent, and you shouldn't expect otherwise. So what I also said, and what I think is important in making the bridge to semi-classical gravity, is that on that side, one should try as much as possible to eliminate explicit dependence on gauge choices and backgrounds to make it easier to compare those two observables from full quantum gravity. So to end on a positive note, I think the focus on quantitatively evaluating and comparing observables is a really fruitful one in quantum gravity that will help us transcend comparing different approaches and ingredients and kind of focus also on the physics. Thanks.
Thanks, Renate. So then, Kasia, do you want to go next and give you a brief summary?
Yeah, so I think the bottom line of my talk was that one can investigate the problem of observables in quantum gravity from the point of view where you start with classical theory and then you quantize it by some sort of deformation. So this is inspired by techniques used in perturbative algebraic quantum field theory. And from that point of view, you can first discuss the question of classical observables and what's the convenient class of observables to choose, and then separate the problem of quantization as a sort of next step. So in terms of quantization, what we currently understand how to do in sort of quantum field theory side of things is to quantize things perturbatively. So one introduces the split into some background metric and perturbation, and then quantizes in a way which is then shown to be independent of that split. So that's the main idea. And that, however, is obviously, perturbative, right? So this is only some shadow of what the full non-perturbative quantum gravity should be. But still, the problem of observables can be discussed there. And now, as far as the choices of observables go, so again, you can, in this framework, you can discuss that in the classical setting. So in the classical setting, you have observables which are local. These are completely out of question. These don't satisfy, well, they are not compatible with the symmetries of the theory. They are not diffeomorphism invariant, so that doesn't work. And then you think about various ways you introduce non-local observables. So one of the main ways I want to kind of pursue is relational observables. So that was one class, relational observables, and then there's various levels at which these could be non-local. And the other class of observables I'm interested in is, well, something which is related to what William was talking about. So edge modes and dressed observables. So this is, I think, in my framework, the least understood class of observables, but I hope that we can establish some connections and see how this fits into the setting. So yeah, so that would be something I would be interested in understanding how my approach connects to what William was talking about in terms of relational observables. I found Philipp's talk really inspiring. So there were many things I would like to follow up, and I'm following up currently. So yeah, looking forward to the discussion. And yeah, that's me done.
Thanks, Kasia. Also, thanks for already starting the discussion. Then, Daniel, do you want to give your brief summary?
Yeah, can I share my screen for a sec?
Yes, sure.
Okay, so yeah, so my talk was related to observables, but the connection was maybe a little bit less sharp, although, well, yeah, so but let me just kind of say what I was getting at, because I think it's still relevant for this series. So I'll accept my, okay, maybe I'll just say it because my my writing pad seems to not be working. So the idea of my talk was that approaches to quantum gravity, I think, can kind of be split into two categories. There are the theories where you try to quantize gravity directly, and then there are theories where you try to quantize something else. Now my, oh, I see. Sorry, now my pad is working, so let me try again. Okay, now it's good. Okay, so so there are two approaches. Or maybe it's still, okay, I give up. I don't know why this is not working. So there's the approach where you try to quantize the metric directly, which in that category I would include things like pure 2+1 dimensional gravity, or Jakiev-Teitelbaum gravity in 1+1 dimensions. And more speculatively, I would say also things like asymptotic safety or loop quantum gravity, I would put in the category of just try to quantize the metric. Whereas there are other sets of theories where what you try to quantize is something else. And so examples of that, so the one I understand the best is ADS-CFT, where you try to quantize some quantum field theory living in a lower number of dimensions. There's also things like the BFSS model, and more speculatively, string theory in general, although we don't really know what that is. So what I was talking about in my talk is that these different approaches seem to be qualitatively different on a number of sort of old issues of conceptual importance in quantum gravity. So in particular, for example, we have the Bekenstein-Hawking formula, S equals A over 4G. We have the idea that black hole evaporation should be unitary, which is closely related to S equals A over 4G. There's a conjecture that in quantum gravity, there are no global symmetries. And then there's also the question of, which kind of underlies all three of those in some sense, which is whether or not we should believe the answers we get from the Euclidean gravity path integral. And so the point of view of my talk was that all of those things are true only in the second class of theories. So in the first class, where we just try to quantize the metric, well, sometimes we don't know if we can do it like in asymptotic safety or something, but in low dimensions, we can surely just do it. But what we find are theories that don't obey any of the things I said. So S is not equal to A over 4G. The evaporation does not lead to a page curve that goes up and down. You can have global symmetries, no problem. And Euclidean gravity doesn't give the right answers. You know, then we just have a question sort of which of these models of how to think about quantum gravity is more likely to be correct in you know, in realistic, you know, not in lower dimensional settings, right? And you know, there we have the problem, of course, that we on either side we don't really have a realistic example that works, right? Like either from trying to quantize the metric or from trying to quantize something else. You know, we don't have a self-consistent theory, you know, in 3+1 dimensions with a positive cosmological constant that's consistent with all the data and so on. Somehow my bias is that all these things I said about S equals A over 4G and so on should be true in the real theory of quantum gravity, which I would view as evidence that well, or at least an argument that the second point of view should be right. But maybe for this panel, I'll just emphasize that I really see this sharp distinction here. And so when we talk about lore about quantum gravity, we have to be clear which of these strategies we're talking about. Okay.
Yeah, thanks a lot, Daniel. And I think it also begs the question whether we can make progress on this distinction or not. Now maybe before we go there, William, do you want to go on?
Sure, thank you. Yeah, so in my talk, I emphasized that while the question of observables is an old one and it's surely important for questions, non-perturbative questions about quantum gravity, it's also something that exists at the perturbative level and can be understood within the framework of perturbative quantum gravity, which is, I think, a potential area for common ground between all these different approaches that we should somehow reduce to some kind of semi-classical weak gravity limit described by what is more or less an ordinary quantum field theory. The key, and of course, in this theory, the problem of observables exists, and it has some non-trivial content, but it's really just it's easily understood as the fact that you can't create some matter or some excitation without also creating its gravitational field. And what makes gravity really different from the other forces is that this can't be screened. And so there's necessarily some non-locality in all of your observables. So I looked at this, the construction of these dressed observables, where you create some matter and with it a gravitational field that extends out to infinity. And so this suggests a picture where your observables are in a sense relational, but relational not to, say, an observer or some other matter system, but to a boundary which you introduce to your system, which could be an asymptotic boundary as in ADS or Minkowski. But I think an interesting possibility is to consider experiments that take place in finite regions and to think about finite boundaries. So since you're asked to pose a question, I think my question would be a more, perhaps an open-ended one, but since we've discussed, in particular, Renate and Daniel discussed non-perturbative questions about observables, I think the question would be what are the implications of having to UV complete these observables for the perturbative theory? So perturbatively, I can write down things which are just ordinary field theory observables, and I can dress them perturbatively. But it seems that if I'm in some setting, for example, where I have to, that these also have to come from a UV theory or maybe something totally, something that's not a quantum gravity theory, but a string theory or something like this. Are there examples where maybe naively I would have written something down which seems like a perfectly well-behaved perturbative observable, which doesn't exist for some reason of compatibility with the UV theory? So thank you.
Yeah, thanks. And thanks a lot for the question also. And then we finally have Philipp.
Yeah, can I share my screen? Can you see this?
Yes, I can.
see. Yeah, so my talk was an overview over relational observables, what they are, how to construct them, what achievements are, challenges, and how they appear in various approaches to quantum gravity. But here I decided that I don't really want to summarize what I talked about in that talk. Instead, can you see this? Actually, somehow it tells me sharing is paused. Sorry.
Yeah, so we can only see the first slide.
Yeah, no, I'm on the second. So maybe let's go again. Sorry. Can you see this black screen now?
Yes.
Yes.
Yeah. Okay. So anyway, so I wanted to rather try to give since we're supposed to have a discussion here, some kind of, I emphasize tentative bird's eye view on how different observables we heard about in this series might fit into one larger picture, in particular relational and dressed observables. And so basically what I'm going to say here, in certain simple situations, I think it is correct. In more generic situations, it is formal in that sense, somewhat speculative, but maybe that's okay for a discussion session. And so basically, one thing that I would like to argue for is that at least in some circumstances, we may be able to consider relational and dressed observables as being abstractly the same objects, just equipped with different physical interpretations. And so the starting point here is, suppose we're given the algebra generated by the diffeomorphism invariant observables of whatever theory we're considering. It may be classical or also quantum. And then, well, one of the main questions is how we are supposed to interpret the elements of that algebra. And in general, that's a very hard question because, at least when you think about them non-perturbatively, these objects are not really functions in space-time, but rather functions on equivalence classes of geometries. So they're not really objects that give you an immediate transparent physical intuition. And now relational and dressed observables are a way of trying to equip the elements of such a set with physical interpretation by introducing a notion of a reference frame, a physical one. It may be asymptotically as in Loll's talk, or it may be some dynamic degrees of freedom in your space-time. And what they do is basically to describe some kinematic degrees of freedom, such as matter or gravitational degrees of freedom, relative to your reference frame. And of course, you can do that in many different ways. So for example, if you choose some kind of reference fields, if you're in 4D, generically we'll need 4 of those. Then we want to know what some kind of kinematical degrees of freedom are when the reference fields read such and such values. Well, that will give us a 4-parameter family of observables because, well, the reference fields, there's 4 of them and they can take different readings. And so these relational observables, they will in fact define something like a trajectory or orbit in this algebra. And if these, in fact, these reference fields are monotonic in a certain sense, then at least in classical scenarios and even simple quantum cases, you will find that you can basically, in some sense, foliate your algebra in terms of relational observables relative to such reference fields. But the thing is, you can also, of course, pick different choice of reference fields, so like a different choice of reference frame, and that will lead to different parameter families of relational observables. So that means I will get different orbits in such an algebra of diffeomorphism invariant observables. And now one can do something similar with dressed observables. We might pick a particular prescription of dressing some kinematic observables, such as a scalar field, by putting a platform at some asymptotic boundary and then shooting in a geodesic and evaluating the field at some particular distance. And again, that will give us some 4-parameter family of observables because, well, we have that's coordinate x in there, but you can also think about it in terms of the parameters that we need in order to localize the platform on the boundary, and also in terms of the distance from the platform at which we're evaluating the field. And so that will also give us some kind of orbit. And if we now evaluate different kinematical observables in this same kind of dressing, that will give us, again, different kinds of orbits in this algebra. But now, just like with relational observables, we can also define different notions of reference frame in the dressed observables case. So giving different prescriptions, such as maybe you want to use perhaps null geodesics to shoot in from whatever your boundary is. to localize fields in a diffeomorphism invariant manner in your bulk. And that will again generically lead to different parameter families and thereby orbits of observables in your algebra. And so why is that interesting? Because well, if we have now the situation that you know, we have some abstract diffeomorphism invariant operator or observable that resides in different such orbits, then, well, one and the same object will come with multiple physical interpretations simply because, you know, each of these orbits comes with a specific interpretation as being the description of some, you know, kinematic degree of freedom, some field relative to your choice of reference. And in fact, in simple cases, this definitely happens for relational observables. I'm pretty sure that this can also be extended to address observables. And so in that sense, you know, one and the same object, diffeomorphism invariant observable, can admit, you know, the interpretation of being both a relational or addressed observable. And that's what I meant when I said that in some cases we may have the situation that they're actually abstractly, as an abstract observable, one and the same object, but equipped with a different physical interpretation. And well, one may ask, why is that possible in the first place? Well, one of the reasons is that we have redundancy in the description due to the symmetries in the game. And because of that, there's in general a many-to-one relation between kinematical degrees of freedom and your gauge invariant degrees of freedom. So there exist many different ways in which we can write one and the same you know, diffeomorphism invariant object in terms of kinematical data. So I'm not sure if I'm allowed to go any further. So I probably am beyond the 2 minutes, but otherwise I could say maybe one. Yeah, I mean, I can stop here if that's. Well,
maybe just if maybe we can kick off if you have a question to someone else, or if you were able to identify something that you found particularly exciting in the other talks, then we could kick off the discussion with that.
Yeah, so I mean, yeah, maybe I have a fairly concrete question to Kasia and on relational observables in her setting, because, you know, generically relational observables are, maybe I should stop sharing my screen. So relational observables in general, of course, some rather convoluted objects when the reference fields that you choose are not particularly well behaved, such as, you know, it may not be monotonic or something like this. Is that, I mean, how do you treat that issue in AQFT or in the perturbative context? Is it that because you're doing it perturbatively, that's not really an issue at that level, or?
Yeah, so you choose a background metric and the set of relational, so the set of reference fields for the background metric which are well behaved, and then you look at perturbations around them. So in the perturbative setting, the idea is that you can find some well behaved configuration of fields where your reference fields are well behaving, and then you consider just a small neighborhood of that, so you don't go too far away from the situation where your coordinate system is good. So yeah, I mean, ideally, of course, one would like to do it non-perturbative, but then there is the question of how these things could behave wildly. Yes.
Can I ask 2 questions of the panel? I don't know, are we at that stage yet? I couldn't quite tell.
Sure, go ahead.
Yeah, so the first is just kind of a vague general question, but then the second will be a little more concrete. So the first is just, you know, once we've constructed diffeomorphism invariant observables, what do we do with them, right? What's the question that we actually care about, that we would use them to answer? So that's question number 1. Question number 2 is specifically in the context of a closed universe, which is, I guess, the most confusing situation for thinking about diff invariant observables. So there's something that's always been a little puzzling to me. So in the standard calculations one does in cosmology, for example, in computing the fluctuations of the cosmic microwave background, you know, you pick a clock, like Kasia was just saying, which is, you know, say attached to the inflaton or something. Like you use the inflaton as the clock, and then you look at perturbations. But like you said, that clock doesn't make sense in arbitrary states because, you know, for a generic solution, the inflaton won't be a monotonic function of time. On the other hand, you can certainly construct the covariant phase space of classical solutions of gravity plus matter in a closed universe. That's a well-defined phase space, and there are functions on that phase space because it's a non-trivial phase space, and any such function is a diffeomorphism invariant observable that makes sense in all configurations. So I find it a bit puzzling that somehow in all the applications I've ever seen, the relational observables always have some very limited regime of validity where they make sense, but yet there are well-defined observables on the whole phase space of all solutions. But it's hard for me to think about what they look like in any practical sense. Like, do we ever measure any of them? Or are they just so like hopelessly non-local that we can't even think about them? Okay, so those are my two questions.
So who wants to start with a potential answer?
Well, so many things to be said in principle, Daniel. So, I think so for the kind of these you said, closed universe, I can't even start imagining what the observables would be. Well, just take, endpoint functions, diffeomorphism invariant endpoint functions, look at Liouville gravity in 2D. I would say, you have perfectly well-defined kind of standard observables. Yeah.
But you integrate over all of space, right? Because otherwise correlation functions aren't different.
Yeah, indeed, exactly. But you keep the, at least, in the Euclidean regime, you keep them at certain geodesic distances. So you have a multi-parameter family, in a two-point function. Everything depends on a geodesic distance. So, and you can just show, for instance, that a two-point function has just standard behavior, even in this very kind of quantum fluctuating situation, with a certain fall-off behavior. So more or less, as you would expect in a standard quantum field theory. And such things, in principle, exist also in higher dimensions.
But is that what we do? Like, am I able to measure the integral of something over all of space-time? That sounds like a hard thing to measure.
Yeah, you see, again, in 2 dimensions, you can do these things barely analytically. Of course, we know.
Yeah, but I'm saying I'm living in the universe. I want to do an experiment. Can I actually measure that?
Well, you look at 2-point functions exactly when you study the early universe, right? You look at 2-point functions, say, of the inflaton field. That's exactly what you do.
Should I really think of those as being integrated over all of space-time? I mean, maybe, I don't know, it's confusing, but.
Yeah, I think it's confusing, but I think part of the confusion is our very classical way, even of, thinking of, a reference frame and coordinates as being kind of drawn over space-time. But of course, that's not the reality even of how we do measurements. Yeah, I would say part of the confusion is already in the classical theory, what we think of as observables. I mean,
that's right,
all of the constructions we make, right, and how we investigate our own universe, these are very non-local, tend to be very non-local operations.
Right, yeah, so my confusion here is purely classical, I agree. I mean,
Yeah, so one should be careful. And for instance, of course, we know that locally you can also always transform gravity away. Yeah, so that already inherently at a classical level makes things somehow non-local. So some of that is not inherent to the quantum theory. But the way we talk about it, the way we do computations, they are often framed just with respect to a coordinate system or a gauge fixing. And that makes it then very difficult to compare them to, say, observables you get from a non-perturbative setting where that reference frame often doesn't exist and cannot be meaningfully incorporated.
Maybe if I could add a data point to this discussion. There have been some discussions in cosmology of exactly the kind of thing that Renate is talking about. So when you talk about the 2-point function of the inflaton, you can, as Daniel was saying, you can go to a surface of a fixed potential, but then you have to ask the question, okay, what do you mean by the distance between 2 points on this surface? And you can construct something which is observable in the sense that a theorist would use it, in the sense of being diff invariant, where you fix the geodesic distance between 2 points. And I think that's very much the kind of thing that Renate and collaborators look at. And you can study the behavior of such things in cosmology. But I think maybe Daniel's getting at the deeper question of observable in the theorist sense versus observable in the cosmologist, of what you actually see. And of course, when you look up at the sky, there's nothing nothing in your experiment that forces those 2 points that you see to be a certain geodesic distance apart on the surface of last scattering. So I think it's to some extent our job to try to construct something that's close to what you would actually measure. So one of the things that I suggested as a future area that I think we could contribute to is trying to construct things that are, for example, something like you start from some point in the late universe and you shoot a null geodesic backward and you intersect the surface. Something more like that actually takes into account something like the behavior of the photons that hit our telescopes. So I just wanted to point out that there's some discussion there, but I think there's also kind of a gap in terms of connecting these diff invariant observables to actual measurements.
Thanks, William. So,
yeah,
Philipp, did you want to continue? Let me just mention that we have a couple of questions already. We have one in the chat and we have some in the anonymous form. But I guess we can give the panel a bit more discussion among themselves if Philipp wants to add.
Well, I just wanted to say something brief on Daniel's question on the covariant phase space. Yeah, sure. I mean, then you have a bunch of diffeomorphism invariant observables, and then the question is how to interpret them. So, I mean, this is obviously a question at the classical level. And so the statement here is that, I mean, probably the vast majority of those observables you would be able to interpret in some sense in terms of relational observables. However, in such a way that depending on your theory, maybe your reference fields can only be used sort of as a locally in phase space as a reference field if they don't have global monotonic behavior. Well, what this will be in general depends very much on your matter content, but there exist, for instance, simple situations where you have certain dust models where you can use the dust as a reference field. And if you were to construct some covariant phase space for that, simply because this dust has very nice global features, you could in fact interpret basically any observable that you have in your covariant phase space as being some relation observable relative to that dust reference frame.
Thanks. And maybe Kasia, do you also want to add to the discussion in particular, because you have a very strict way of defining?
Yeah, sure. So first of all, the question about what can you do with these observables? I think I can say something about that. So, I mean, it was already mentioned about the inflaton. So the obvious way is to use it in cosmology. And this is something I have looked at with my collaborators to use, well, a class of these relational observables on Friedman, Robertson, Walker, where for time you also obviously use the inflaton, and for space you use some non-local observables defined using the Green function for the Laplacian on the spatial slice. So from that point of view, I think computing various higher order corrections in cosmology using observables that are diff invariant up to all order might be an interesting direction. So yeah, so what we have done was, we didn't renormalize it up to our order, so that's still, I think, something that should be done and could be done. And then also use these observables for other effects, where you want to look at the quantum gravity corrections to, let's say, Newton potential or things where, you don't expect these corrections to be terribly huge. Okay, so that's my part of the thing.
Maybe that's a good point to bring in one of the anonymous questions, which is addressing that, Kasia, you presented and emphasizing nicely a perturbative algebraic QFT formalism. And the question is whether there are key issues in generalizing this formalism to non-perturbative or even discrete approaches.
Oh, discrete approaches is very easy, actually, because some of the difficulties are really sort of renormalization and singularities. So one discrete approach, which is very natural in that regard, is causal sets. So, I mean, in terms of okay, I mean, this is not, again, the full theory of quantum gravity, but if you just want to have quantum fields on a causal set, you can use exactly the same methods as in perturbative algebraic quantum field theory, but then, yeah, you avoid all the technical difficulties, so that's great. Yeah, in general, I would say the idea of deformation, quantizing via deformation quantization is also applicable to non-perturbative discrete approaches, but well, the causal set is the one I'm kind of looking at the moment, but it would be interesting to also look at other discrete approaches. Now, on continuum, we have the same problem as we have with quantum field theory in general. So things like Yang-Mills theories don't get quantized non-perturbatively unless on the lattice. So there is like a big, open problem in mathematical physics, how to quantize interacting quantum field theories non-perturbatively in 4 dimensions. So I guess we would run into the same problems with an extra problem on top of that observables are weird. So there is an extra non-locality and possibly extra singularities coming from the kind of observables we look at. So it's a difficult problem, but yeah, maybe not entirely hopeless, I would say.
Yeah, maybe there's a connection to what Renate has been saying. But let me also mention there's questions by Claudio, Axel, and Joshua in the chat. So maybe let me just start with the first one. Claudio is asking whether he gathered correctly in Philipp's talk that relational observables are defined with respect to a space-like hypersurface, and whether relational observables could then also be defined with respect to future light cones.
Well, I mean, so the way relational observables, the way I presented them, I mean, so they were constructed in the ADM formulation where you use spatial hypersurfaces. But, they're not really localized necessarily on spatial hypersurfaces. So in the end, I mean, you should really think of these objects rather as being defined in your phase space. So there are ways, there are functions really on the orbits. You should really rather think of those as such objects. Now coming to your question on light cones, I think that was what you were asking, whether you could write them down on light cones. So the thing is, these relational observables, since they are really very non-local objects, you can't really say that they're localized on a light cone or any particular point in your space-time, because well, they're highly non-local objects by being diffeomorphism invariant. So and that goes back to the comment that I made before, that you shouldn't really think of these objects as being functions in space-time, but rather functions on equivalence classes of geometries. But then maybe you're interested in asking about like causal relations or something like this between different localizations in terms of relational observables. And well, at least at the classical level, you can have that, you have something like commutation at space-like separation, but where space-like separation is really now defined in a relational way. So I'm not sure if that answers your question, but in any case, the main point is that just being diffeomorphism invariant objects, you shouldn't really think of these objects as being localized on any kind of hypersurface or like a light cone or anything like that.
Well, okay, but I mean, my question was more sort of within the entire light cone, or so. I mean, that is the light cone itself is a non-compact object, right?
Yeah, sure. But I mean, these, they're not even really localized in such a light cone. I mean, they're, most of these observables, they're something like an integration over all of space-time. So in that sense, you should not really think of those objects as being functions in space-time, but they're, at least if you think about them non-perturbatively. So if you go perturbative, like in Will's talk or in Kasia's talk, then there's a way in which you can think about them as being localized in your background space-time. But if you go non-perturbative, then you can't really do that. Okay. So in that sense, so that's why a priori these objects, these diffeomorphism invariant objects, and that's not just about relational observables. It's more general. I mean, they're not particularly intuitive at first when you think about them, that they're kind of functions on equivalence classes of geometries rather than in space-time.
All right. Then Axel, do you want to maybe just unmute and pose your question? That might be easier. All right. If not, then I'm just going to read.
Yeah, I can do it.
Okay.
Sorry, I just had to move the chat away from the unmute button. Yeah, so one of the things which also with respect to tracing, so we have general relativity in the classical frame where we know what different invariants mean. So one of the things is, of course, talking about quantities which are manifestly by construction different invariant. So I gave as an example things like the curvature scalar, which is invariant, and then interpreting them not as a coordinate transformation, coordinate dependent quantity, but as something which is calculated for a certain event, would create something which is local, manifestly different invariant, and has a well-defined classical meaning. And of course, we can construct the same thing in any quantum theory, and therefore I would just pose the question: such observables would be not something which we can define across different approaches and would use.
So I think if you want to say that something like the Ricci scalar is invariant in the sense of depending on an event, you have to specify what event you're talking about, right? So it could be, for example, the value of the Ricci scalar at the point where such and such scalars take these values, or where a certain, particle collision happened, or something like this, right?
I mean, events are the underlying objects. Like, for example, in causal sets or so, you have also this notion of here are a bunch of events, and then I have relations between them.
Right, but they're not labeled in any way. If you wanted to ask, right, if you wanted to ask a question about the curvature at a given point, you would have to, you need some way of saying telling me which point in my causal set to talk about. In particular, if you have a quantum theory, so right, so I'm going to have many causal sets, right, in my ensemble or my path integral or whatever I do. And if I want to talk about an observable, I have to pick out the curvature on each one separately.
Of course, I mean, the important point is when you want to do a path integral, then you would say, okay, I take a definition which says, okay, I have two events, and then I require them to have a certain geodesic distance on average between them. Something like this. It's of course something which is generally new. We need a possibility how we can talk about this, but I mean, we need anyhow a labeling in a way which is diff invariant to really talk about.
But the thing you just said is not local, like because if you use some geodesic or something to say where something is, right? Then if you put something in between, the thing moves, right? Like from the point of view of the coordinates.
But this is exactly the same thing which you also have in classical physics. I mean, also in classical physics.
Well, you mean classical gravity or classical, let's say, electromagnetism or something?
Anything. Absolute positions don't have any importance.
No. But absolute positions mean even less in a different variant theory than they do in theories that still have inertial frames of reference.
Yeah, but the point is that fixing something absolutely by having just a single argument is of course a generic problem which doesn't make sense in any kind of physics. So of course, if you want then to say I would like to have fixed information or something like that, then of course in the end I have to make it relative to some other object.
But it's somehow easier to pick a Lorentz frame globally than it is to pick,
but a Lorentz frame is not something which I can define diff invariant, right? Because then I choose a coordinate system already.
I'm not sure what to say. I mean, in quantum field theory, usually we view Lorentz transformations as global symmetries, which are, whereas in
but
gravity,
also they're
gauge symmetries. So they have to be, observables have to be gauge invariant. It's kind of a different.
Yeah, but the important point is just like this. I mean, also for if even there, you have the problem how there you just have the situation that events and coordinates are equivalent. That's the advantage in non-relativistic theories.
but no one disputes that you can point to a location in space or space-time, be it Newtonian, be it relativistic, and just call it X, right? And then do the average over all field configurations and zoom always in on that point X. But the problem is in gravity that you cannot really do this, right? So that would also dispute that there is therefore it has to do with the non-locality of the observables, clearly. And I think I share a feeling that I think William voiced in his talk a while ago, with these constructions, of a field having a certain value, wherever Riemann is 12 and Kretschmer is 15. I don't think they're really local, because you still have to scan, right? You have to scan your space-time in order to find these places. So I would actually dispute that these are local quantities in the standard sense of local fields, in fixed background QFT.
I agree with Renate 100%. Maybe one way of saying that might help is that in ordinary quantum field theory, we have a fixed background metric that's not dynamical, and we can define observables relationally to a background field. But in gravity, we have no choice except to define them relationally to dynamical fields. That's the difference.
Yeah.
All right. Axel, unless it's super urgent and you want to say something, I think I would move on and also give Joshua the chance to ask his question. Again, if you want to, you can just unmute.
Sure, yeah, thanks to all the presenters. I think this is a very nice and productive discussion. Yeah, my question is just that there's a possibility, one could at least imagine, that the fundamental description is not in terms of geometric degrees of freedom. Daniel made this distinction, I think, that right, we can quantize gravity, or we can imagine that gravitation somehow emerges from a different description. From that perspective, is there any reason that there must be an abstraction to local observables, and whatever the fundamental description is, from which some semi-classical geometric description with gravitation emerges?
Does anyone want to go first?
Well, I guess since I said that, I can comment on it. But yeah, so that's a good question. Somehow, emergent gauge fields work a little bit different than emergent gauge symmetries work in a bit of a different way than emergent global symmetries. And usually when you have an emergent gauge symmetry, it still has to be exact. So for example, in one way you can think about it is that either you have a graviton with consistent, without a longitudinal, modes, or you don't. And so if we think that in the infrared you have a massless graviton, then you have no choice but to have exact diffeomorphism symmetry, even in a situation where the graviton is emergent. And okay, it's a little bit hard to think about emergent gravity, but like if you look in condensed matter systems, there are plenty of field theories that have emergent gauge fields in the infrared. Just like scalar field theories, but like somehow because of strong coupling, there's a gauge field in the infrared. And when you look at those, the photon is exactly massless in the infrared, even though it's, there's no photon in Lagrangian. And I think that would be the case here. Certainly in ADS-CFT, it's the case because the graviton is dual to the energy momentum tensor in the boundary theory, whose scaling dimension is exactly D. So that tells you that the metric is the graviton is exactly massless in the bulk. So you need diff invariance.
Can I ask the question this way then? You can imagine that in the fundamental description, the diff invariance is just local. There's no geometric notion a priori, and therefore there's no sense of active diffeomorphisms. And if there's just local coordinate reparameterization invariance, does it then require that observables be non-local, or is that necessarily a consequence only of active diffeomorphism invariance?
Well, I'm not sure the difference between active diffeomorphism and invariance and local. I mean, yeah, we can think about diffeomorphisms either actively or passively, but that's just how we talk about them, right?
Okay, I have in mind a theory in which there's no geometric notion, but still a local invariance, which is simply local coordinate reparameterizations. And I'm just not sure that, well, perhaps you can explain why it is that
such a framework would require non-local observables. Perhaps I'm misunderstanding, but I thought the logic for requiring non-locality of observables was that you can move points from point to point. If there's no a priori notion of geometry, then I can't imagine moving point to point.
So where does your theory live, Joshua? Does it live on a space or space-time, or what is it?
I can write down, for example, a theory which is coordinate reparameterization invariant that has fields, phi of x's, but there's no space-time metric.
Yeah, where do the fields live? On something, or?
The fields are functions of coordinates x that live in R, d and d dimensions, but there's no a priori notion of a space-time metric. The theory is, I mean, you can do this. Start with just a free theory in a curved background and with an auxiliary space-time metric. Integrate out the auxiliary space-time metric by imposing t mu nu equals 0. You get a new theory, which is just like. This is just a specific example, right? But a toy picture. But then you get a square root of determinant of d nu phi Lagrangian, which has no space-time metric appearing it anymore. It's been integrated out.
Let me make a comment here. So, are you familiar with Neuter's second theorem?
Yeah, of course.
Yeah. So, in Neuter's second theorem basically says that anytime you have a symmetry which is labeled by a local function, then you're going to have constraints. And if you have constraints, that means you're going to have some kind of symmetry that you have to quotient by in order to get a consistent dynamics. So it sounds to me like what you're saying, you would still have to quotient by I mean, the question is, do you quotient the pre-phase space by these transformations to get something physical? And if you do, then you're stuck. If you do, then you're stuck with non-local observables. And yeah, and I think you're going to have to in any situation where it's labeled by a continuous function, because Neuter tells us that.
Okay. Yeah, I think you can also maybe see it in another way, because I mean, if you have local coordinate reparameterization invariance, and then you have some kind of diffeomorphisms on the space that are labeled by these coordinates, something like an active diffeomorphism, then you can of course always write that when you write it in coordinates, in fact, as a coordinate transformation. And then, so if you are invariant under local coordinate transformations, then you basically also have to be invariant under such active diffeomorphisms, and that will bring you then to non-local observables.
Yeah, thank you.
Let me maybe just briefly announce that we asked the panelists for keeping a 90-minute slot, so we can go a bit longer with the discussion. But yeah, so that everyone knows that it's like gonna last, I guess, about half an hour longer. And then we had a question also, an anonymous one, regarding whether one could implement relational observables in a discrete sense. And I guess that's a question suited for Renate. So maybe you want to comment on relational and
yeah, I want to comment first on the notion of discrete, right? I mean, discrete, one should reserve to fundamental discreteness, so to people who really believe, on the Planck scale, they're little, finite size building blocks of whatever shape and form. Yeah, but I don't belong there, I just want to say. So I'm just following the standard kind of, critical systems logic, where you just, you look for phase transitions in statistical systems of dynamical geometry. Yeah, so about relational observables, am I allowed to ask a question? I mean, they seem to be very much favored by my co-panel members, the DREST and the relational observables. Now, looking at that from a kind of non-perturbative point of view, one runs into difficulties, and it's not so clear whether they are just technical or of a principal nature. I suspect the second. Yeah. So all of these relational observables, they require a detailed control on the analytics of, G mu nu, tensor calculus, require really kind of, smooth constructions. I think Philipp called them convoluted observables. That just means they're extremely complicated in terms of functional dependencies in a way that I just don't see could, possibly be implemented in a non-perturbative regime. So, but I have a similar, so kind of through the back door come in questions about, okay, what are those degrees of freedom at the Planck scale, and how do I describe the physics there? And a similar picture, I would say, with dressed observables, right, of the type that Will talked in his talk. These are also objects that are known to have a very bad behavior. Let me just pick out the Wilson loops under renormalization. They satisfy certain algebraic relations, but they tend not to be preserved under renormalization. So again, one runs into kind of issues of principle if one really wants to extend it beyond perturbation theory. Yeah. And that also brings me to a question that he specifically asked: what is the meaning of perturbative observables anyway? Are those meaningful? Is it just a technical thing that whenever I compute kind of H-bar effects on my favorite classical observables, they turn out just to be so small that I cannot even dream of ever measuring them, like perturbations of Newton's law or something? Or is there something more intrinsically wrong or not very useful, thinking about perturbative observables? So are the real kind of true quantum observables that exist kind of non-perturbatively of a quite different nature? So maybe we are kind of barking up the wrong tree. So I'm happy to hear anyone speak up for the relational and dressed quantities.
Kasia, is that raised hand?
Yeah, I think I can speak up for both. Well, so first of all, in classical theory, classical gravity, we know what are the non-perturbative observables, right? So that's clear. Now, the way I want to view perturbative observables is, take those objects and then embed them in the theory quantized via some sort of deformation quantization. So the idea of deformation quantization is that you don't change your set of observables. You actually don't do anything to your vector space of objects you want to measure, you want to describe, and you only change products, brackets, and other algebraic structures there. So I actually don't care how complicated these things are, because the complication in my viewpoint is not on the side of observables, but really on the side of being able to define the product. So define the quantum product of the theory, so something which gives me the commutators and so on. So which is the big issue, right? I mean, this is where the randomization enters, and this is hard. And yeah,
but that is if everything is linear, if all observables are linear, in your favorite variables, that's not an issue. But
if everything is linear, if everything is linear, then it's great.
But this is just not patently not the case. So then you get into exactly renormalization issues.
Yeah, exactly. So it's not linear. But what I'm saying is that the complication in building that product is, well, somehow separated from the complication of building your observables. That you can say, okay, I want to quantize this and that observable. It doesn't mean that you have to do anything to that particular, classical functional that describes that observable. You have to change the way you multiply it with another one. So it's not, I'm not saying that this is obvious or easy or done, but I think I'm just trying to maybe slightly argue with saying that it's hopeless and it doesn't even make sense to talk about those, because I think it does. I mean, you can say what's perturbative observable here. So it's just, your classical observable in your quantized theory where you deform the product. So if you could deform the product non-perturbatively, then that would be non-perturbative theory of Young-Mills or quantum gravity or whatever. If you, deform your product perturbatively, that's your observable in the perturbative theory. but it still makes sense to talk about it. It's
well,
I mean,
don't know.
what I'm trying
We
to
don't
say.
know before we haven't done it, right? So it may just not exist.
Well,
that non-perturbative product you are dreaming about, it may
right.
not
It may not exist in quantum field theory either. I mean, people might be like completely wrong by trying to construct Young-Mills non-perturbatively. Maybe it doesn't exist. I mean, maybe we're all led astray. But that wouldn't stop us, I'm afraid.
Do you really think that's a live possibility? I'm just curious.
To construct Young-Mills non-perturbatively?
Yeah. I mean, that would be kind of
I can answer, but you have to stop recording.
I mean, there's a big difference between. I mean, Yang-Mills theory is renormalizable, right? So that seems pretty different from gravity.
Yeah, no, it's renormalizable, but it's also only perturbatively renormalizable, right? I mean, going from perturbative to non-perturbative is hard. I mean, we don't know so many quantum field theories non-perturbatively in higher dimensions. There's like, I mean, yeah, if you're asking me about like, okay, so what are the perspectives for non-perturbative? I think it's a hard question also in quantum field theory proper.
Well, yeah, but like say for QCD, right? Like you can do numerical simulations and match.
Oh yeah, I mean, yeah,
experiments.
Yeah,
so that looks pretty good, even if mathematically we can't quite convince ourselves it's all under control, right?
Well, you can do numerical simulations which are based on some kind of lattice theory, right? When you discretize things. So, I mean, maybe the way out of this is, okay, so we say that there is fundamental discreteness. So, like, just give up this business with trying to construct quantum field theory non-perturbatively and just go ahead and do, let's say, causal sets. But yeah, so if you give fundamental meaning to that discreteness, then of course there is no problem.
I mean,
right?
in lattice QFT, they try to take the continuum limit, right? They don't succeed.
They're trying. Yes, that's correct.
But as they get closer, it looks like the answer is converging, right? I mean, this is what they say, right?
Yeah, right. But yeah, that's still, it's still finitely many lattice points you can simulate in a finite computer. There is a I think, I mean, on a more serious note, I think there is a fundamental difference between how finite systems behave and how infinite continuum behaves. So, and you can, as I said, you can avoid talking about infinite continuum if you believe in fundamental discreteness. But if you don't, it's not. It's an indication that things work out, but it's not a guarantee that things work out.
Can I just ask Claudio, is the raised hand related, or is it a new question?
It is sort of a new question.
Then maybe if anyone in the panel wants to still comment on the topic of going non-perturbative with relational observables.
Well, the question seems inextricably linked to the question of whether it makes sense to quantize the metric non-perturbatively. If you in things like ADS-CFT, where you quantize something else, there are clearly observables that make sense non-perturbatively, but they don't particularly look like dressed functions of bulk matter fields and so on. Those seem to only make sense up to exponentially small errors, in ambiguities. And so at least in that situation, we would just say these things don't make sense non-perturbatively. They're just kind of true up to exponentially small. They make sense up to exponentially small ambiguities, which in some situations may matter.
But Daniel, I gave some examples of where you have perfectly well-defined, seemingly non-perturbative observables that are neither relational nor dressed.
But I don't know what it means to have them if you don't have a theory that's non-perturbatively well-defined.
Well, you have them in the sense that it goes beyond. You have a framework when you compute things that are get close to the Planck scale and seem to deliver reasonable results. It's a computational framework. You can think of it as a gravity analog of lattice gauge theory, indeed.
But I mean, in any theory where you're viewing the Planck scale as a cutoff, you're necessarily perturbative, right? Because the thing you're expanding in is energy divided by m Planck. So if your theory is constructed as an expansion in energy divided by m Planck, I just don't know.
It isn't. It is a lattice theory. It is a lattice theory of dynamical geometry. So it's not constructed in that way.
Oh, well, yeah, sorry. So if you have a theory that's constructed based on, well, let me see if I say this in the right way. So yeah, so if you just quantize the metric, you can try to make non-perturbative observables, right? To the extent that your theory makes sense.
Well, as I said, take 2D, Daniel, take 2D Liouville gravity. Does that make sense to you?
So in 2D, I agree. So then it makes sense, right? So that was this bifurcation of theories that I had. So there are theories where it makes sense to just quantize the metric, and 2D gravity is like that. And then yes, these things make sense non-perturbatively.
Yeah, and you have non-perturbative observables, which are neither relational nor addressed.
Yeah, I understand. Yeah, but then in higher dimensions so far, the only examples we know are cases where gravity is emergent. And then my comment was just that, or at least there's only an effective theory, and then I don't know how to ask the question about.
But the question is to some degree independent of whether that non-perturbative, UV completion exists. It only needs to exist, at high energies, and you have exactly the same questions.
Well, but the answer is
you ask and answer in 2 dimensions. So it's a question of principle. Do certain quantities, do they make sense, and are they kind of finite?
Yeah, so I guess I would say non-perturbatively the metric doesn't make sense. So anything that's constructed out of metric by relational things, that won't make sense either non-perturbatively. But that's in theories where you quantize something else. In theories where you quantize the metric, it might, if quantizing the metric makes sense, like it does in dimensions.
Quantize the metric is maybe not the right way to call it, but you still have a notion at very high energies of distances and volumes. That's of course a much weaker condition than G mu nu in any sense or even effective being well defined. So that's a different ballgame.
Yeah.
But I guess we can summarize this as Daniel is basically just saying that there are 2 types of different ways of defining quantum gravity, and one might be the one where you intrinsically define it as a theory of the metric, and the other is where you define it as some external framework that generates the metric, right?
Yeah.
So
but the question of observables also remains, right, in that other framework. So what
of course, but the observables may not look like what we're calling relational observables here. I mean, those may only make approximate sense in an emergent scenario.
But you still want to relate them, I guess, also to, kind of whatever quantum corrections of some quantum gravity phenomenology in the end.
Yeah. Mm-hmm. But the observables that make sense non-perturbatively won't be these ones. They'll be the ones that are defined in the boundary theory. That's all I'm saying. I'm not saying.
Yeah, that's fine. Again, let's classify it under. It's a different ball game.
Yeah.
Yeah.
Can I just briefly ask whether other panel members want to add? Otherwise.
Well, maybe I'll just say that you can kind of flip Renate's initial question, right, about whether these perturbative observables make sense. I'm okay if somebody tells me, look, well, these dressed things that you build don't actually make any sense in the UV theory, and I'll say that's great. Tell me, what does make sense in the UV theory, and I'll expand it around a flat background and ask if it has any meaning for perturbative physics. So I mean, it seems ADS-CFT has some preferred things to look at. I mean, generally, there are things that live way at the asymptotic boundary, but there are other things that can be constructed. So maybe there is some sort of more natural notion of a local observable that you can build, and perhaps the same is true for CDT. But I'd very much like to know, okay, which observables should we be focusing on?
Yeah, I mean, I think most of it has already been said. So when it comes to relational observables, I would agree that, these are objects that make sense when you have a metric. So if you have a theory that isn't fundamentally a quantization of geometry, then relational observables will only really make sense in an effective regime. And so, whether they're objects that are valid at the Planck scale or not, that's a different question. However, yeah, in effective theories, I mean, they're valid constructions, and I think they are probably also maybe useful for phenomenology. But it's true that, yeah, if you want to look at like really genuine non-perturbative constructions of these objects, I mean, they're going to be horribly complicated objects, and it may be true that yeah, depending on the framework or on the theory you're working in, that maybe these things don't really exist non-perturbatively.
All right, Claudio, now maybe you want to go ahead.
Yeah, so the question that came to my mind with respect to non-locality is sort of whether that tells us anything about the way. So if we accept that in a theory of quantum gravity that gravitational observables should be non-local, whether that tells us something about the way, at the level at which gravity emerges from a fundamental description. And maybe to motivate what I'm thinking is essentially whether this tells us that gravity has to show up sort of as a next to leading order effect. For example, like you have for light, you have the gravitational spin Hall effect that is only an integrated effect. So you don't observe it at leading order. And the reason why I've been thinking that is that in the causal firmament system framework, it is exactly the case that gravity sort of shows up at next to leading order in the regularization length. So you sort of, I'm wondering whether these sort of things might be connected or not, or what do you think about it?
Whoever will.
Yeah. Well, yeah, maybe I could just say, just to comment on the sort of perturbative orders of things. So I'm not sure I totally understood the question, but I think I could say that the effect that you get from maybe just make the point that the effect that you get from non-locality of observables shows up in the commutator. You know, you'll find a lot of statements in the old literature saying, you know, well, if you want to define things at space-like separation, of course, things at space-like separation commute, but there could be a chance of a fluctuation, you know, pushing one point into the future light cone of the other or something like this. And that's some non-perturbatively small effect. But maybe just to re-emphasize the point that actually there is a perturbative effect, and it appears at order G. So depending on how you count the orders, it's kind of natural to treat your perturbative parameter as the square root of Newton's constant. So in that sense, it's second order, I guess, but they're order G Newton effects coming from dressing to commutators. I don't know if that partly answers your question.
Well, I mean, it was more sort of a quite of open question. I didn't. It's just something that has been sitting around in my mind. I was just wondering whether any of you have some thoughts on that. So
maybe because we only have a couple of minutes left, and at some point we should come to some form of closing. Let me use Dingxia's question to sort of circle back to the bigger picture, because he's asking whether it's possible that the questions about quantum gravity observations, which I guess will be the topic of the next series, and the question of observables in current discussions rather detached. And I guess that's part of our job to bring these closer together. So maybe I can ask the 5 panelists for brief closing statements, also with respect to what they think is a good idea in bringing these two things closer together. And then Sumati, I hope that Daniel will be able to answer your question a bit more as well in his statements. And we can probably now go the other way around and start with Philipp.
Okay. Yeah, I mean, at the moment, I mean, as of course many things in quantum gravity, they're kind of far detached from observations. And I mean, when it comes to the construction of observables, I mean, there's of course, I mean, very technical questions associated with it, and very and also conceptual questions about the meaning of these objects. Of course, there, first of all, one doesn't really worry about observations at first, but ultimately we should get to that. Yeah, now when it comes to observations, okay, I mean, some have already mentioned it. I mean, when it comes to cosmological observations and the CMB, or when it comes to inflaton, I mean, there are, for instance, relational observables that are actually being used. So that's some kind of indication that at least in effective regimes, these objects are in fact useful and they're physically meaningful. But indeed, what is really lacking is a systematic way of relating these observables to something that we can interpret physically as something that is measurable. And in fact, maybe another thing that is kind of missing is, in some sense, you know, something like a measurement theory for relational observables, or maybe even for other kinds of observables, or an observation theory of them, what it would actually mean to you know, to observe or measure some of these objects. And so in order to have some kind of systematic quantum gravity phenomenology, I think a lot more work needs to be done in this direction. There are some kind of promising starts, in fact, in the AQFT literature. In fact, it comes from York by Chris Fuster, who are looking at, you know, they're kind of introducing notions from quantum information foundations like quantum operations into an AQFT setting and a diffeomorphism invariant setting to describe measurements in such a regard. It's still a bit far away from quantum gravity, but I think those are developments that we should definitely push much further.
Thanks. And William, I don't know if you want to add to our closing.
Yeah, sure. I mean, I think, no, I think it's good to end talking about what could actually be observed. And so one of the things I think we touched on already is cosmology, where you actually do need to take into account fluctuations of the graviton. There is I should say, of the gravitational field, and there is a sense in which we are actually, you know, actually doing quantum gravity measurements, even if they're very simple ones, which are well understood. But I think there is, you know, as we want to push those things to greater precision, we do need to think about this question. It's not just a question of principle, but really a question of practice to understand how exactly which gravitation, you know, invariant gravitational objects we are measuring when we point our telescopes at the sky. And then the other thing, I think, which we haven't mentioned so much, is the is implications for scattering, and that really it's, I think, been more greatly appreciated in recent years, that there is a real influence of quantum gravity perturbatively just in the infrared, and that it is important to consider dressed quantities even for S matrix, you know, ordinary scattering the way you would do in your QFT textbook. And I think that's another avenue, whether you'll actually get observational effects, okay, that I don't know, but it's at least a framework where you can talk about things that are in principle not just observable, but observed, even if the gravity corrections are very small.
Yeah, thanks a lot. I guess Daniel is already starting.
Hi. I guess I don't have too much to say that I didn't say already. Maybe one thing I can comment just to sort of advertise a little bit. So my postdoc and I are about to, maybe in a week or two, put out a kind of epic paper, epic in terms of length, I don't know if quality, about the algebra of dressed observables in Joukhiv-Teitelbaum gravity and matter in 1+1 dimensions. And one of the things that maybe is worth mentioning is that we're able to use the algebra to sort of illustrate several physics points about how gravity works in 1+1 dimensions and connect to various ideas about chaos and strong coupling in the dual boundary description. So one aspect of that may be interesting is there you're actually using the non-local diff invariant observables in the bulk to to model strongly coupled dynamics in the dual boundary description. And so it's kind of running in the other, I mean, usually I'm someone who tries to learn about quantum gravity, but here's at least one way of trying to relate these different variant observables to experiments, but kind of in this convoluted way where it's experiments in the dual theory, boundary theory instead of, you know, which somehow are most naturally thought about in terms of these different variant observables in the ball. So hopefully in a week or two that'll come out. Yeah, I'm not sure if I have anything else to say at the moment.
Thanks. And Kasia?
So two things. One thing is that, well, because of the nature of this perturbative AQFT framework, if somebody finds, you know, tomorrow or in the course of the next lectures in the series, like nice observable that can be observed. So if there is something that gives like a good outlook for measuring and finding quantum gravity effects, it is relatively easy to you know, throw it into the theory as long as you have a classical description. So that's maybe the advantage of the formation quantization framework, that it is easy to throw new things in and then see just how they work. Now, measurement theory, thanks, Philipp, for mentioning that, because I think that's a very important point, that even measurement theory in quantum field theory is kind of, you know, at the beginner stage. And I would definitely recommend the works of my colleague, Chris Fuster. Also, there are things about kind of related to relational observables by Frenhagen and Renate. So they have a work on time in quantum mechanics, which is essentially saying how to think of time as a relational observable in quantum mechanics using AQFT methods and measurement theory. So there might be some combination of these two things that kind of maybe leads to some sensible measurement theory for relational observables. So maybe that's another avenue for investigation. Okay, and yeah, I'm looking forward for the next series of talks here.
Thanks a lot. And I guess, Renate, you have the final, or almost final, I will have the final word.
Okay, let me give it a try. So in answer to the question, I think the quantum gravity observable, yeah, story will be very, very important to connected to real physics. And of course, us making actual predictions is also very important. And I think to some extent being opportunistic and looking, you know, where a specific, you know, let me favor non-perturbative formulation leads us, and what are the objects that can be simply accessed quantitatively within a given approach, should then, you know, hopefully form a bridge. Let me give an example. Of course, the spectral dimension, everyone has been computing spectral dimensions not too long ago. I mean, people, you know, looking at gravitational wave signals and possible imprints of quantum gravity have come up with very kind of simple models of how a non-trivial spectral dimension might be reflected in gravitational wave signals we receive. So that's just, you know, an example of maybe one wouldn't have thought about even, you know, hadn't it been for these developments looking at spectral dimension. So there are a bunch of things we do not understand. I mean, the list is long, but an essential one is, I think, how do gravity and matter degrees of freedom interact? What are the dominant degrees of freedom kind of at the Planck scale? Is matter important at all? And anyway, how do they influence each other? So is our somewhat naive, you know, extrapolations from what we know to be the case at LHC energies, you know, across all the dark unknown zone, yeah, are they correct? Are we being misled, or is that the right way of thinking about it? So the matter coupling is essential and obviously relates to quantum gravity phenomenology, because it's not pure gravity we are observing, but there's matter involved somewhere, everywhere.
Thanks a lot, Renate. Thanks a lot to actually all 5 of you and everyone in the call. Yeah, I just would like to advertise again the next series. I guess it would be great if part of the Observables audience would be present in an observations setting to maybe find a way to get these things closer together. And I guess with that, thanks again to everyone, and have a nice rest of your day, or how short ever that is in some places. All right. See you all.
Thank you. Thanks for
Bye.
organizing this. Bye.
And thank you, Aaron, for doing an amazing job chairing today.
Yeah, thanks, Aaron.
Yes. We should have applauded the panel also, but applause for everyone.
See you.
Bye.
See you.
Bye.